Hey guys, welcome back, and in this experiment we will be designing application of precision diodes along with op amps. So the first application is a half wave rectifier. So we have seen the rectification already. So what happens in half wave precision rectifier is that the schematic looks like this over here. Just have a look over here, half wave basic precision rectifier for designing of a 50 Hz. So over here I have just used a single diode over here. What happens in this, that the output waveform being generated is like uh, only the half part, the positive part of the input will be generated and being observed towards the output part. There won't be any negative part of the generation being created at the output. So as we see the half wave, this is just the half wave. There's nothing when the negative input has been going through. It's flat, almost it's zero. And again, it only works for half part, that is the positive cycle. If we would change this diode into a reverse direction, then it would have only worked for negative part. So over here it would have been flat line, then a sine wave, again a flat line, and again a sine wave. But what over here is that a input is given and it only has been working for positive part. So this is a half wave precision rectifier. But what if we modified it by using one more diode? The main advantage of doing is that the accuracy, it won't be seen clearly in the at the frequencies of 50 Hz, but as we go down over here, let's say up to 1 kilohertz, yeah, you can see the output over here. This is for I think 1 kilohertz. Yes. So what happens is, just have a look at these input. These are getting like spikes over here, and if we see over here, it's a proper sine wave, a proper half wave precise rectifier. And the main difference is over here, if you can see, it's a spike, it's coming like pulses. But if you see over here, yeah, this is a proper sine wave. There's a bit of a disturbance and a noise generation over here, distorted. But the half wave which has been precisely rectifier, the half wave precision rectifier, if we modified it by using one more diode, then we can see a proper sine wave over here. It's not like that we will be getting the spikes over there. So at low frequencies it's not easy to see the basic difference amongst all, but as we increase the frequency we can see the differences. Now for a full wave rectifier, this is a circuit, two op amps being used and two diodes being connected across it. So over here, if you can see, this is this is the whole input voltage, the blue line which you can see, and the output is for full. There's no cutting over here, there's no clipping, nothing. It's a full wave rectifier. So this is the main rectifier which is being used nowadays. So now talking about clippers, we want to clip off some of the input voltage. What we will be doing over there is, as we are using a precision diode, that clearly makes that clearly mentions that the reference voltage should that clearly mentions that the input voltage is should be less than the 0.7 of the diode. As the normal cut-in voltage of diode is 0.7, the input has to be almost equal to, less than or equal to 0.7. And for making sure this sine wave input which I have been given, the Vref, this is actually a reference voltage, has to be less than the sine wave signal. So this is for a positive clipper at Vref is positive. You can see the Vref is positive. I have clipped off this part. I have clipped this much amount of part from this circuit. So now for minus Vref, we just have to make this as negative. So once I make this negative, I will clip off the negative part of the signal. And for negative clipper, what we do is we change the direction of the diode directly, and then we can see that the negative part over here, if you can see the output. So over here I have clipped off the negative part and the final one over here. So this is how the clipper circuits work. Thank you so much.